Okay, let's start. So we start with one ID equation. So for those that are not here last week, you can go to Moodle. So inside Moodle, there is one. First of all, make sure you guys are in Moodle. Okay, make sure you guys are in Moodle. And then you go to EEE 315. And then there's a class recordings. So you click on class recording inside the folder. There's week 1 recording. So I already briefed week 1. I already briefed the group assignment and final project during week 1. All the questions are already there. So please go back and check what actually happens. Okay. If you got any question, you can ask me after the class. So now coming to regions of operation. So the last week, we actually stopped until here. So we get an equation on drain current. So we say this drain current is equals to half mu NC ox W over L, VGS minus VTH square. Okay, but actually, it won't be the same all the time. It won't be this drain current the same all the time. It depends on which region that they are operating at. So generally, we can say there are deep triode region, and saturation region. Okay, deep triode, and saturation region. So we know that when VGS is more than VTH. So remember, we have one point that when VGS is, we need to make sure our gate voltage is very high, more than the threshold voltage, then only the transistor can turn on. So when transistor turn on, we don't care whether there's drain voltage or not yet. But as long as VGS is more than VTH, we say that our drain current is this one. So this is the first conclusion that we have done. So we said that the drain current will be mu NC ox W over L VGS minus VTH times VDS minus half VDS square. So we can say that the drain current is being affected by your gate voltage and also being affected by your drain source voltage. So that's for your triode. Okay, you just need to remember this is for your triode region. And then your deep triode means that your VDS, your drain source voltage, is very, very much lower. Very, very much lower. Okay, to recall, we say that this is our transistor. We got drain, source, and gate. So if we only got gate voltage, we will somehow have a channel first. So if the gate voltage is already more than the threshold required voltage, we will have a channel, but we won't have any current flowing. So the amount of this current flowing depends whether how much our drain voltage and source voltage is flowing. So let's say our drain voltage and source voltage, now source is 0, drain voltage there is something, then current can flow from drain to source. So now if you already got the channel, VGS already more than VTH, but our drain voltage is so much lower. So this is not really enough to push it yet. So we call that a triode, deep triode region. We call that a triode region. Okay, deep triode region is because VDS is very, very much lower than 2 times of VGS minus VTH. So it will push much slower. So you can see in that case, our half VDS square we can basically ignore because VDS is so small. So this half V minus half VDS square we can ignore. So this will be our deep triode region equation. ID equals to mu NC ox W over L VGS minus VTH times VDS. This will be our linear region. So it's our deep triode region. We say linear is because we are observing at this straight line only. So if you want to follow V equals to IR concept, we have our V over here. We have our VDS over here. We have our ID over here. So we can say that VDS over ID, we can say this is the resistance of this instrument. The resistance of this transistor when it is in deep triode region. So we rearrange our equation, it will be 1 over mu NC ox W over L VGS minus VTH. So this will be our, what we call R on, the resistance of this MOSFET. Okay, so just to let you know, so in conclusion, this transistor can act as a voltage dependent resistor. Voltage dependent resistor. Why do we say so? It is because when we increase our VGS, the whole resistance drops. Okay, when we increase our VGS, this resistance is 1 over VGS, so it will drop. So we use voltage to control the resistance of this device. Next, if it is saturation, so we have gone through triode region and deep triode region. The next region is saturation region, which is the most important region for our designs. We usually need to ensure that all our transistors are in saturation region. Then only it will work well, especially for amplifiers. Okay, so saturation as in when VDS is more than VGS minus VTH. When VDS is more than VGS minus VTH, that is our saturation region. So we see again this diagram. We got our VG that is already more than your threshold. Now we got also our VD. So what if we keep on increasing so much our drain voltage that it is now more than the threshold, more than VGS minus the threshold. So I think the last class over here, we show this. We say that, okay, you see now, if this is VG is 1 volt, my VD is 0.5. So the difference between them is 0.5. My VG is 1 volt, my source is 0. The difference between them is 1. Okay, that's why we say the current density seems to be like this. There's more charge at the source, there's more charge at here than at here. So you can see the line roughly already. Okay, so we can see. So you can roughly see the charge over here is so much more, and then it goes lower, 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 lower all the way. Okay, so you can, let's do this. So you can observe it is actually like this. Okay, it is actually like this. So there are charges in this red color area. So here is because they are still sticking. This part, they are still sticking because it is 0.5. Okay, you still got a charge of 0.5 difference. But right now, you keep on increasing this probably until 1.3. You increase your drain voltage until 1.3. And then your drain voltage maintained at 1. So 1 minus 1.3, basically here got nothing already. So you cannot use this diagram anymore. Okay, you cannot use this diagram anymore. We will say it will kind of pinch off. Okay, so exactly when your VDD is equals to VG minus VTH, it's supposed to be like this. Okay, it's supposed to be like this. This part is left a little bit only. But if you increase more than that, this part will straight away go the other way. It will straight away go until here. It will straight away go until here. So you can see this part basically break off already. So we go like that. You just imagine my drain voltage suddenly push too hard until all the charges go the other way and then leave a space in the middle. So that's what we call the saturation region. So since now the new diagram, it looks like this. We got this length over here already. Okay, so maybe we will need to change our equation. Because remember last time our equation, it depends on the whole length. We say that is the length from 0 to L until your drain. But now your current, your charges didn't really reach until your drain, but it reaches where it is somewhere over here. It didn't reach to all the end. So we need to change a little bit of our equation. We say that our ID in terms of the effective length over here, okay, our current that flowing in this length is, instead of from 0 to VD, it is from 0 to VGS minus VTH. It is until somewhere here only. It didn't go all the way until VD. So we will rearrange our equation and then we will get this finally. So this equation is the saturation region equation, which the one that we see most of the time. Okay, our current will usually have this behavior. So the extra drain voltage, okay, let me just increase this size. We say that the extra drain voltage, it doesn't increase the inversion region. So the inversion region means the channel's point. It did not really increase, okay, because it already pinched off. But the pinch off point moves further back. So it will shorten the what we call effective length. So you can see this part is being shortened all the time when we push more and more. So this part becomes shortened. Okay. That's why current is approximately constant. Okay. That's why current is approximately constant. Now we go back to this. Okay. So we can see deep triode is supposed to be a straight line. When VDS increases, ID increases. But after that, when triode region, so when it is already turned on, and then we increase our VG slowly, our VDS slowly, it will go up like this until a peak point, because we got a square over here. So it will peak somewhere at here. But when VDS is much more than VGS minus VTH, we're already over that point. So you will see it's supposed to be almost a straight line already. Because no matter, so you can see from this equation, saturation region equation, no matter how you increase your VDS, there's no equation related to VDS in this case, right? So you got VGS, you got VTH, you got mu-NC-ox, but you don't have VDS. So even though you increase your VDS, it's supposed to be a straight line. The drain current will maintain. That's why we say this is the more ideal case for us, because we want a stable current. So far, any question? Okay, the next one is what we call second order effect. Second order effect. Okay, this second order effect, it is a bit special. Just now, remember I say that the saturation region, the drain current supposed to be a very straight line. It won't go anywhere related when we increase drain voltage. But actually, it will due to channel length modulation. So this is the first second order effect. Due to channel length modulation, we might need to increase a little bit of our current when our VDS increases. So this is the diagram. From deep triode to triode, supposedly, ideally, it is a straight line. But due to channel length modulation, this thing will go up, slightly up. Okay, why? So you imagine that this thing becomes shorter and shorter and shorter. But when we derive IV characteristic last time, okay, we assume the length is the whole length. We assume the length is whole length. So just now we settle the part where drain voltage, we don't use drain voltage anymore, where we don't integrate from 0 to VDS, or we integrate from 0 to VGS minus VTH, but we haven't settled the length part. Here, this length is supposed to change. So this 0 to L is not really the L anymore. It is the L depending on your drain voltage. So we say actually it is changing. That's why we have to include it inside. So we don't care how it changed, but they have come up with one equation that half mu-NC-ox W over L VGS minus VTH squared is your saturation region formula. And then you have 1 plus what we call lambda VDS. You need to multiply with 1 plus lambda VDS. This is your channel length modulation. The lambda is your channel length modulation. So it is just a coefficient, because we know that the whole thing might get affected by VDS slightly. So we add one more term behind so that we can tune back to the really correct one. Okay, it is because when VDS increases, length decreases. That's why we need to add this. So we can say that ideally, the add-on is change of VDS divided by change of ID supposed to be infinity, because this line is a straight line. But now we have a finite value. Okay. So you might think we mentioned last class that our sizing, our transistor sizing gets smaller and smaller every time. That's why we are changing from a very big room of computer to a small device like our handphone now. So it is all due to the length. Okay, they are decreasing the length every year to half of the previous length. So how does this affect us actually? So we can think of like, why do we actually need this length? What happen if we increasing the length? What happen if we don't decrease the length? So we want to study why. So generally, for analog, it will be, for analog, we would like ideal current source, which is a straight line for analog. So it will be better if we have our length longer. It will be better if we have our length longer, because you imagine that initially the ratio was this long, and then because of channel length modulation, the effective length is only this part, but it's still very long. But if you're using a very short one, and then suddenly you drop by a lot, because of the channel length modulation, your effective length become much shorter. Then this part is the only part that can conduct current. The channel length modulation, the blue color part that go up, it will go more further up. So this is not ideal for us. It is not ideal for analog. But for digital, it is actually very good. Okay, we want the shorter the better, because this long, digital need to switch from 1 and 0. If we need to switch from 1 and 0 between this length, so we need to go so far away and then go back, go so far away and then go back. So for digital, they cannot switch fast. But if the length is very small, they can straight away go in and out, then it will be much better. That's why we say for channel length modulation, second order effect, due to second order effect, analog devices would like it to be as large as possible for length. Digital would like it to be as short as possible. The next one is what the next second order effect is what we call body effect. So when we say second order effect, means the not really very ideal effect. Okay. So the other one is what we call body effect. So why do we say body effect? We mentioned that for body, the fourth terminal of your PMOS or NMOS, we will connect them ideally to, for NMOS, ideally to ground, for PMOS, ideally to the higher potential. Okay, but what if, let's say we only study for NMOS now, what if our body in NMOS, it is not grounded? What if our body in NMOS, it is not grounded? Okay, so body means this part of it. Okay, so basically it's your P plus. So when it is grounded, okay, I think I did put, okay, so when it is grounded, so P plus is basically 0. Okay, when this is ground, we say P plus is 0. So here we say it is 0. And then now we put some voltage at the source or your drain. Anyway, okay. So let's say at your source, you put some voltage. Let's say it is 1 volt. So does it look like this green color diode? Because it is a PN junction. But now this one is actually low. This is actually high. Okay. Give me a second. Okay. So we say that if VB is equals to 0, the depletion region exists. So we will say that we need to go back to the PN junction. Okay, let's go back to PN junction. This is your P now, this is your N now. Okay, so now if your body is 0, and then here I didn't attract anything. So basically both are like ideal, okay? So this is also 0, let's say. Your source, this is your source. This is your drain. So at this stage, what will happen? We say that even there is nothing connecting in between them, connecting for drain and source, in normal PN junction, we're supposed to have what we call a PN junction, right? What we call a depletion region. So we will have the depletion region, okay? But if VB is more than 0, so if we increase this part, if we increase our body, then this depletion region, it will be smaller, right? Because because there's more voltage pushing through your N side. So the depletion region becomes more and more smaller. So we say that it is easier to form a channel. So this part becomes smaller and smaller. So basically, the resistance between your drain source and the body becomes lower because it is more voltage pushing through already. The region becomes lower already. The current can attract to the other side more easily. But if VB is more than 0, so now VB is lesser than 0. So now if we say our VB over here, we put it negative. What happens? Our PN junction, we always need P larger than N. That's the ideal case. But now your N is 0, your P is negative. So we say that instead of electrons attracted to the upper place, the holes are attracted to the substrate instead. So the whole depletion region becomes wider. So ideally, what do we want? We will want our ideally we will want our body connected to ground. However, sometimes if we really need to reduce our VTH, we will need our body connected to somewhere slightly larger potential. Okay, just slightly above 0 will do. We cannot put too much because it will break. So if you accidentally put your body voltage much lower than your source, then it won't be good. Is it confusing now? Yes. Confusing. Okay. Not sure if this can draw. Okay, can. So let me just draw it out a little bit about the body effect. Okay, channel length modulation, is it still okay? So we will say about body effect only, like why does it happen? So ideally we want our VB to be 0. Okay, we have 3 cases now. VB equals to 0, VB lesser than 0, and VB more than 0. So ideally, we say that we have our NMOS here, and then you can just say the whole thing is PMOS. Yeah, the whole thing is P, N and P in the middle. This is your substrate. So here, we know that it will form something called depletion region. Okay, so we take this out. Here we got our P. So we observe at this point. Okay, we observe at this point. So we will have our P, we will have our N. So P now is connected to 0. N is also 0 because N is our source. We usually connect source 0. So generally here we have a depletion region. So that's okay. So you will have depletion region first. And then in normal case, when there's depletion region, and then when this upper part will the gate pull some of the current. So when gate voltage is high, is maybe 1 volt, it will help to attract all the electrons over here to the top. That's the normal case. Okay. Here, although we know there's depletion region, it will stop a little bit, but it will still attract up. But if now VB more than 0, VB more than 0, if you still observe this part, you realize that initially the depletion region is somewhere over here. But now, because VB more than 0 already, so now maybe here become 1 volt, here becomes 0. This depletion region, will it become smaller? Yes, because it's a PN junction, so it becomes smaller. So in between them, this distance becomes smaller and smaller. So we can say every electron basically pull up. Okay, so they are somewhere floating more nearer to your end. And then when I put my VG up, so I put a 1 volt here, these electrons can be attracted easily to the top, more easily. Because now the depletion region becomes lower already. My electrons, instead of floating at the bottom, they basically go towards nearer the top part. Then when VG increases, my electrons can easily attracted up. So we say VTH is lower than before. This is the normal VTH case, the threshold case. This is VTH becomes lower because they can easily attract up. But if your VB becomes lesser than 0, so VB becomes lesser than 0, this is -1, this is 0. Then this looks like a reverse diode. Then this region, this distance between them becomes so much larger that the electron may be just only at the very, very bottom. Okay, this is normal, so there is still somewhere at here, but this is almost at the very bottom. Then it is very hard to conduct, so that is the highest VTH one. Okay, so you don't really need to know these formulas because these formulas are quite complicated, but these are, I just put there for your information. Okay, so the next one is transconductance. Transconductance. So we say our MOSFET, NMOS, PMOS, transistor, MOS device, all these terms I use the same, I mean the same thing. So all these transistor that convert a voltage to current. Our MOSFET, our CMOS device, that convert a voltage to current. Because you remember we say we increase voltage and then we get current. So we are converting the voltage into current. So we say that they have this transconductance characteristic. Okay, if they are blocking, then it is a resistance, right? But they are conducting, so they have a transconductance characteristic. We call them GM. GM is the transconductance characteristic. It is the 1/R, inverse of your R. Okay, resistance, it resists the electron flowing, but conductance means it shows us how good it can conduct. So in this case, we say that whenever we change some voltage, we will get this current. So it is the derivation of ID divided by VGS. So it will tell us how much the output current changes in response to a change in the input voltage. So basically, let's say we have VGS over here, and then we have ID over here. Okay, so let's say after the what we call the threshold voltage, the graph goes like that, go up. So at the first circle over here at the bottom, compared to the top circle over here, which one is actually a better one? We would say the top one is the better one, because we only need to change a little bit of our gate voltage. We can change by a lot of current already. We can generate a lot of current already. But over here, if we change this much of voltage, we cannot change so much of current. So this is the slope of the graph, the gradient of the graph. So this GM, we will use GM term many times. So this GM is the main thing that tells us how effective is our MOSFET in terms of converting the voltage to current. So this GM, we will need to derive, we can derive into 3 ways. Okay. The first way is we want to derive in terms of GM versus VGS, gate voltage VGS. Okay. So we have our formula just now. Still remember, this is what formula? Saturation triode. This one, if you cannot recognize, you just check whether it has VDS. It doesn't have any VDS term inside, then it's saturation region. So this is our saturation region formula. We take this, we say that GM is the derivation of ID versus VDS. So we derive, okay? So we differentiate this whole term, because this whole term is your ID. We differentiate this whole term with VGS, okay? Because it's ID versus VGS. We derive them, and then we will get our GM to be, because these two move here already, so mu n CoS W over L, VGS minus VTH. So this whole term become this one. Okay, so now we get our GM to be mu n CoS W over L, VGS minus VTH. Okay, we just derive this term basically. Okay, we derive this term with VGS. Okay, so now this term, we draw a graph. We draw GM versus VGS. So after threshold, we realize that it doesn't have any square or anything. So basically, it will just be a straight line. When VGS increases, your GM increases. When this increases, there will be a straight line. So this is your first characteristic, first GM characteristic. There are another way, the second way. We can say that ID equals to mu n CoS W over L, VGS minus VTH squared. Okay, so what if I just move this half to the left hand side? So instead of times 1 over 2, I move to the other side, so it becomes 2ID mu n CoS W over L VGS minus VTH squared. So this equation and this equation, they are the same thing. Then, so basically this is still our saturation equation, and then we will do a little bit of magic over here. So we want to find in terms of VGS minus VTH. So we move this term to here, and then the rest, it will be 2ID divided by mu n CoS W over L, square root 8. So these two are the same thing, yeah? And then we will find what exactly is GM. Okay, we mentioned before, in the first case, GM equals to mu n CoS W over L. So mu n CoS W over L we maintain from the first equation. But now, VGS minus VTH, we change it. We change to this VGS minus VTH. So we move this thing down. Okay, it's because now I don't want to find its characteristic in terms of VGS anymore. I want to find its characteristic when my drain current changes. So this is if we fix W over L constant. So we get this equation in the end. So you realize that if I fix my width and length, and then I draw in terms of ID, I draw my GM versus ID, you realize that the more the drain current, the more the GM, but it will reach some point, it will be saturated. So this is your GM versus ID characteristic. The other one is and let me think, where am I now? 2ID VGS minus VTH. Hold on. How did I come to this equation? Mu n C ox W over L, VGS minus VTH. Anyone can solve this? I suddenly hang. I'm not sure how we come to this equation. I know this is GM, mu n C ox W over L, VGS minus VTH. But where does this 2ID versus VGS minus VTH coming from? Oh, okay. So that would be very complicated. Hold on. Sorry, give me a while. Or anyone able to solve this, you can let me know also. My question is, where is this coming from now? I mean, this is your GM. This is your GM. Oh, okay, sorry. So basically, we say 2ID is equals to mu n C ox W over L VGS minus VTH squared. So 2ID divided by VGS minus VTH squared. 2ID divide by one of it. So I cancel out this. Divide by VGS minus VTH squared. It will just be mu n C ox W over L VGS minus VTH. Okay. Somehow not sure what happens. Okay. Get it? Okay. So we can say that GM, because this was our first GM, so GM is equal to 2ID over VGS minus VTH. So now we don't want W over L. I don't want to see W over L in my GM equation. So I keep my ID constant. If I keep my ID constant, you realize that GM goes down with VGS minus VTH. So the larger your VGS minus VTH, the GM not so sensitive anymore. Okay, so these are the three transconductance equation. Okay, it might be coming out in quiz, but I haven't set the quiz question, so I will let you know where to study once I have done the quiz. So I will let you know, like, you need to know what the transconductance, or maybe you need to derive ID and so on. Okay, so don't worry, we will go step by step. Okay, the next one is biasing in MOSFET. So we say that when gate source voltage is lower than VTH, the gate is not on. ID is equal to 0. And then when VGS more than VTH already, ID start flowing. But every time we observe, we are observing in terms of DC voltage still. We say that, or we pump a 1 volt DC source over here. And then my ID start flowing. So if you pump a DC source, your current is supposed to be a DC also. It won't suddenly go AC. So you can imagine the first case, if you pump a DC gate voltage, you get a DC current, ID over here. So if your VGS is that low, your ID is supposed to be somewhere at the top. Okay, but we don't usually deal with DC. DC is just to turn on your device. AC is the thing that you want to amplify. For example, amplifier. We're amplifying something AC to something AC. Like when I talk to my mic, it is accepting it and then converting it to something louder voice. So it is from AC to AC. So our final aim is still getting the AC signal that we want. So you can imagine that I still maintain my DC voltage, but I add on one AC, very small, so I put VGS, small gs. I still add on with that. So instead of just a straight line now, I have a threshold DC bias point, VGS, big VGS. But now on top of this, I have my AC signal, small VGS, go up and down, up and down. So what will be my current in the end? My current supposed to be a sine wave up and down also. Make sense? Because at here, you put a straight line, you get a straight line. So now you put something up and down, you should be getting something up and down on top of the straight line just now. Okay, so the general formula for saturation, it was this one, half mu NC ox WOL VGS minus VTH squared. But instead of it's a VGS now, I would say that it is supposed to be your VGS, big VGS plus small VGS, your DC plus AC voltage. DC plus AC voltage. So now it becomes half mu NC ox WOL VGS minus VTH plus VGS squared. This one, we plus with it already. So it will be half mu NC ox WOL. We can separate them out. We say VGS minus VTH square plus. So usually we need to, you see, if we square the whole term, we need to square inside also, right? So we will do 2 times 2 already, times 0.5 already, becomes mu NC ox WOL VGS minus VTH times VGS. Okay, and then this whole term VGS heaven square. So this is just your normal maths, like your A plus B square. So you will have your A term first. So it will be A square plus 2AB plus B square, right? So this is your, the first term is your A square. This is your A, and then this is your B. First one is your A square. Second, 2AB, 2 times half AB. Okay, A and B. And then third is just the small VGS, B square. So you get a graph, so you get an equation like this now. You get equation like this now. So what exactly are these? So the first one, the first equation, the half mu NC ox, this this yellow equation is your normal DC voltage, DC current that being generated. And then the last one, I mentioned VGS is a very small AC voltage. So this VGS is very small. This is probably just the noise, the distortion. Okay, so we say this is distortion, but this is the main part. We say that it will be the big VGS times with the small VGS. So this is what we call GM VGS. Okay, if you can recall just now when we derive, this term is your GM. Mu NC ox WOL VGS minus VTH is your GM. This term was your GM, the first GM that we derived. So this is your GM small VGS. GM VGS. Okay. So if it come up to these three equations, add up. So we say when VGS is very, very small, if VGS is very small, the noise is very small. So basically VGS square can totally ignore. But if VGS is very large, if this is very large, something very large, you square it, it will be much, much, much larger. Then it will be very significant. Okay, so for example, we have our ID versus VGS graph over here. Okay, ID versus VGS graph. So after VGS reach its threshold point, only we start to have current, correct? So we have this graph. So we look at some point. We look probably at this line first. Okay, we look at the red color line, straight line. So we say that initially, this was our big BG point, and then we add on one VGS. We add a small VGS. Okay, this small VGS we add already. Then corresponding to the top, we realize that we will get the small swing over here. This is my output current. Okay, when we have this input VGS small swing, we will also have this small swing at our ID. But what if our swing is very big? We have a very big VGS now. So you see now, I'm still starting at the same line, but I have a very large swing now. So refer to this swing, we go up. You realize that now your voltage, your current output is something like this. Okay, because we want to go down all the way, but it cannot go down. You realize at this point, this is the what we call being cut off. The voltage range is being cut off by here. So this is what we call the distortion. Because it limits it already, the VGS is so big, it started to have distortion. We say this is the distortion. This VGS is too big, so started to have distortion. We only got our upper signal correct, our bottom signal being cut. Okay, so this is the what we call, the other term is what we call the voltage headroom. Voltage headroom. Okay, voltage headroom. It means how much it can swing up and down. Okay. The next one, the last part for your chapter 1, the last part for chapter 1 is what we call device model. Okay, so we know that, I think you all draw small signal model during when you learn BJT, right? So here also the same thing, we are drawing small signal model, but instead of small signal model, we will also have what we call a large signal model. Okay, but you can just ignore, you can just assume they are similar things. Okay, when we say large signal model, basically we assume it is a very large signal only. When we say small signal model, we assume our VGS is very small. Okay, but most of the time we are testing small signal model. Okay, so for small signal model, let's only see small signal model. We will assume that signal is changing with time, a very small signal. And then the first step to draw small signal model is we want to turn off DC, turn off all the DC signal. Okay, basically we say that this was the equation just now, but we added the channel length modulation. Okay, so we say that we ignore the DC, the whole DC line. We only want to know what is the small changes in the current. What is the small changes in the current? Okay, so you will have this one. You have this diagram. First of all, this is NMOS. For NMOS, we have gate, drain, and source. So we will draw at the top two lines. It will be a gate, it will be a drain, bottom will be your source. Gate and drain are at the same line. Bottom is your source. And then we know voltage allows the current to flow from drain to source. So it will be a current source already. Your transistor is basically a current source. So we need to draw a current source. This is a current source symbol that connect from drain to source. We call them ID. Okay, this is the current flowing. The current that is flowing, we call them GM-VGS. The current that's flowing, we call them GM-VGS. Okay, which means that, oh, my VGS is controlling how much my current flow depends on GM. That's why this current is called GM-VGS all the time. Okay, and then here is just a VGS. Here is open. The gate and source is open, so we call this VGS. Okay, this is the ideal case. Ideal case where there's no channel length modulation, there's no body effect or anything. We will need to draw small signal analysis many times to analyze stuff. The second one is when we consider channel length modulation. So when we say lambda is not equals to 0. In that case, we say that channel length modulation happens is because instead of the drain and source ideally connected together, we have a gap between the drain and source. So a resistance somewhat occur between drain and source. So we have to add, on top of this, we have to add one more R. We call it R naught. Okay, this is usually for channel length modulation, R naught. We have one R naught connecting between drain and source. And if body effect is also included, okay, if body effect is also included, this might be complicated if we want to go through the equation, but we just need to know that if body effect, if body voltage is more than source voltage, so VB more than 0, VTH drops. VTH drops. So that's the ideal case. Okay, when VTH drops, ID increases. So basically, we can say that the change of your body and source voltage will cause an increase or decrease in your current also, your drain current also. But we don't directly affect our GM-VGS over here. We add on one more IDB. This drain current also flowing from drain to source is either positive or negative. It depends how we connect our body. So this one we will call it GMB VBS because it depends on your body to source voltage. And then this is GMB. This is how much our body can affect the body voltage can affect the current. GMB VBS. So this is the full model. If you say you want to include for all non-ideality, this is the full model for your small signal analysis. We have gate, drain, parallel line. Bottom, there's one source. From drain to source, there's GM-VGS, there's R naught, and there is GMB-VBS. But actually, our small signal model, sometimes we won't be stopping at here. Okay, but we discuss this further at the frequency response chapter. But you can see that since this is the yellow color are the conduction point. We have metal over here. We have n-type material over here. So these are the conduction point. When there's one conduction point, and then there is something in between, dielectric in between, and then there's the other conduction point, then it looks like a capacitor. It's just like two conduction points inside there is dielectric. It looks like capacitor. So we say that from gate to source, there's capacitor. Gate to drain, there's capacitor. Gate to body, there's capacitor. Between source to body, there's also capacitor. Drain to body, there's also capacitor. So there are capacitor everywhere. So if you really want to go through the full model, it will look something like this. Okay, that has a lot of capacitor. But up to chapter 4 also, we don't need to learn this one yet. Okay, we only need to learn about the capacitor afterwards. So this is just for your information. Okay, now we will have 7 minutes break. We'll start again at 12:10. Anyone is not in Teams or anyone not in Moodle? Okay, no. Okay, so we have know the basic of transistor. We already know mainly there are three regions: deep triode, triode, saturation. So you need to know the three equations. But generally, the most important one is saturation region. You know that it will only work after VGS more than VTH. And then saturation region is stay between when your VDS is more than VGS minus VTH. So now we need to use the single transistor to build amplifiers. There are different types of amplifier. Okay, so we will learn common source amplifier. There will be 5 types of common source amplifier. And then there will be common drain amplifier, and there will be common gate amplifier. But why do we need amplifier? It's because the signals are generally very weak. Okay, maybe we have a temperature sensor. Maybe it only change a little bit, maybe few ohm when temperature change by a lot. So we need to amplify this signal so that it can be useful. Okay. Also, we sometimes amplify it so that we can overcome noise. We want signal to noise ratio to be as large as possible. So we need to enlarge our signal so that the noise still low compared with our signal. But in analog IC design, nothing is perfect. We cannot actually tune until everything is good, because it follows this whole diagram, which if you want to have low noise, okay, if you want to slide toward your noise, maybe your voltage swing might be very bad. So they are all interconnected to each other. Impedance, power, noise, linearity, gain, supply voltage, voltage swing, speed. All those are connected to each other. If you want low noise, probably you will need to trade off your speed. So there's no ideal case, but we can only tune to whichever that we want. Let's say our sweet spot is we want to make sure that the supply voltage is very low. So we can only tune until the rest maybe not that good, but supply voltage is good. So coming to the first real circuit is what we call a common source amplifier with resistive load. Common source with resistive load. Okay, so how do you draw it? Okay, so we will draw one NMOS first. NMOS diagram. So this is your NMOS at the bottom. NMOS diagram. And then this is your drain, this is your source. Drain to source. When we say it is a resistive load, means it's a resistor. We will have one resistor at the top. We have one resistor at the top. We call it RD. Okay, so if we go, we will put one VDD. When we say VDD, it is the highest voltage point, the voltage source. VDD, we connect to a resistor, connect to your drain of your NMOS, and then your source connect to ground. Where does your input coming from? The one that I speak, the one that I amplify. Here is your input. The gate is your input. We call that Vin. Okay. So in the end, we expect to get an output. So the output, we haven't analyzed, but now I'll be telling you that the output will be inverted. For common source amplifier, the output will be inverted. If your input is this one, your output will be 180 degree out of phase. Okay, but a bigger one, a bigger swing. Okay, so now we will examine a few things. Okay, so to make sure you guys know what exactly is common source, the common means usually we ground them. So you realize that your source is now grounded. So common source with resistive load means you do know, you forget which part that you need to ground it, you just ground your source. Input is always at the gate. Okay, output is at the drain. Output is at the drain. Okay, so now let's go part by part. we say that when V in is equals to 0, if your V in is 0, then will there be any current flowing? Your VD is 0 means your gate is 0. So gate is 0 means there is no current flowing. So what will happen to your V out? We say the V out over here is your VDD minus this current, right? This voltage, right? VDD minus IDRD, it will be your V out. VDD minus IDRD equals to your V out. But what exactly is your ID? There is no voltage from your gate, so there's no current. So no current, no ID. So ID is 0. So your V out is basically VDD. Your V out now is your VDD. Okay, it's straight away your VDD. So you can imagine when V in is low, is 0, your V in now is already at this maximum. Your V out now is already at this maximum. So looks like they are inverted already. Okay. Then if we increase, so when your VDD is now more than V in minus VTH. Okay, so or we should say this, if we increase our V in more, so now our gate, our M1 now turns on. Our transistor now turns on. If we slowly increase this, our transistor turns on. So current starts flowing. Current starts flowing. But right now, VD is more than VGS. VD is more than VGS. Okay, so VD more than VGS, this is your saturation region. VD more than VGS is your saturation region. So VD minus IDRD is still the V out. But now VDD minus, what is your ID now? Because we say now transistor is saturation region. So we just plug in the saturation region formula. This is our saturation region formula. Half V NCOS W over L V in minus VTH square times RD. So what you will observe? We think that my V out might decrease exponentially, right? Because of the square over here. So my V out will decrease over here. As V in increases, due to the slope, due to this square, my V out will decrease something like this. Okay. When this V in keep on getting larger and larger, you realize that VDD minus something larger becomes smaller and smaller. So V out decreases. This is your saturation region. And this is the point that we want our amplifier to work at. This is usually the point that we want our amplifier to work at because we want to observe a change. When we change one input, you see there's a change, big change of output. Okay, this is the point that we want to observe. But what if now you keep on increasing your V in a lot until it is more than VDD? So your VGS more than VDD now, then you force it into triode region already. So the formula changes. You force to triode region, the formula becomes, the ID formula becomes this one, that you have VDD over there. You have the VDS, basically it's your VDD. So you realize that now your V out will drop much slowly as V in increases. As V in increases, we don't have the square anymore, but the square is at VDD now. So if your V in increases, VDD minus something that slowly increases, the V out will drop much slower. So you will see over here, triode region is still decreasing, but it is much slower already. Okay, so the main point, your transistor, the amplifier will only work in saturation region. Because when we say amplifier, it means that we want to observe a gain. A gain in terms of a change of output over change of input. A change of output over change of input. So when in saturation region, our change of output is this formula. Our change of output is this formula, VDD minus half something. So we put it over here. VDD minus half mu NCOS W over L something RD over change of input. So if we differentiate this whole equation with V in, you will get negative mu NCOS W over L V in minus VTH times RD. So the negative term is very important because this is your VDD, VDD minus. So that's why we have one negative after we differentiate it. So you will see in the end, you get your gain to be negative mu n C ox W over L, V in minus VTH times RD. So what exactly is your mu n C ox W over L V in minus VTH? This term over here, it is your GM, the first GM that we derive. So this is what we call the transconductance. So if we simplify it, we say that our gain for common source amplifier with resistive load, it is negative GM times RD. The RD is the resistor that we put up there. So from here, we can observe, what if we want to double the gain? If you want to double the gain, we can increase our RD 2 times. Okay, but we know that nothing is ideal. So maybe after we increase the RD, something might happen. So let's say if we increase the RD a lot, the blue color one is the normal RD. The blue color one is the normal RD. But if we increase the RD a lot, means the total biasing point gets lower because there's resistance. The total biasing point gets lower. So now it cannot swing so much anymore. So you will have a bottom cap below. So if you increase, then maybe up there still okay, but the bottom, it will be capped because it can only go down maximum until the VTH. But now you want to decrease some more, so it cannot go down, okay? So we say that the gain might suffer. Okay, now we will go into small signal analysis. So for all the amplifiers that we'll be learning, we will need to draw small signal analysis. So we just want to analyze what happens when we increase a little bit. So what we can observe. When we say you want to draw small signal analysis for amplifier, in the end, we want to get the gain. We want to know what is the small signal gain, V out versus V in. So our point is V out versus V in. So first, we're not sure how to draw, but we already got this black color. You see the black color part only of this circuit. This is our basic common source with resistive load. So first, we can start with drawing the transistor. So if you don't see any point, we draw the transistor only. Okay, so we have our VG. We say transistor, we got a gate, drain at the same line, source at the bottom, and then there's one GM. We say this is GM VGS. Okay, then now you will observe. My point was, if we want to draw small signal analysis, we need to ground our DC source, any DC source. The DC source over here is only VDD. So we will ground this DC source. Okay, and then we will see. So first thing, after the drain, we realize that there is one RD. There's one RD that connect to ground because we ground our DC already. After drain, we have RD connect to ground. So after the drain, we have RD that connect to ground. And then this point that at the drain, this point is also our V out. So V out, go to drain, go to resistor, go to ground. Go to my RD, go to ground. And then my V in, can I ground it? My V in I cannot ground because this is AC. So I will pump a very small V in over here to my gate. And then gate to source, it is always open. This is what we call V in. Plus minus, this is our previous VGS, but now it is V in. Okay, because this is our V in source. So meaning that we also saying this is basically our previous VGS. Our VGS is also what we call V in. So GM VGS now is GM V in. GM V in. Is that okay so far? From that, convert to this only, okay? So now our aim is to find out V out over V in. our aim is to find the red color part, V out versus V in. So what we can do, we need to find their relationship. Okay, we can find the output node. We can choose any of the node. Okay, but we only got one node over here, which is this one. So if we see at this node, we will see that the current that goes out, we do KCL over here. The current that's go out, it's GMV in, right? This GMV in is also the current that go from here, that goes from here. Okay, so, or you can just say any current that go out, supposed to be the same. We can say the current that go from RD, it can only flow to GMV in. So you can say GMV in is equals to, instead of writing the KCL, you can also say my GMV in is equals to my, here is your V out, here is your ground, 0. So your current flowing from bottom to top, and then flow to your GMV in. So it's equals to my 0 minus V out divided by RD. Is that correct? It is flowing from 0 to V out, and then all the way to GMV in. So the current that go up is equal to the current that go out. So now you got V out already. So you got negative V out over RD equals to GMV in. Negative V out over RD equals to GMV in. So we want V out over V in. So you put the V out, you put the V in there. So in the end, it becomes negative GMRD. Negative GMRD is your small signal gain. So you realize, oh, this is my small signal gain. Any questions so far? Okay, the second one. What if I say now there is channel length modulation? What if I say there's channel length modulation now? Then what will happen? What will happen? Okay, so when we mention there's channel length modulation, let me just delete this. Okay. When there is channel length modulation, what do we need to include? We need to include R0, the R0, the small R0 over here. We say that this R0 is supposed to go from drain to source. My source is now grounded, so I just ground it. Okay, so the whole thing is exactly the same as just now. I only added one R0. I only added this term over here. So this is my small, the channel length modulation, my lambda, these are not. Okay, so after adding this, how do I check for my V out now? We can say GMV in now, the one that go to here, it will be the current that flows to these two parts. Basically 0 minus V out divided by R0, and 0 minus V out divided by RD. They both are in parallel. So we can say it is negative V out 1 over R0 plus 1 over RD is the current that flow, add up both of them, and then flow to GMV in. So you rearrange GM, this whole thing you move down, equals to negative V out over V in. So in the end, your gain, V out over V in, is equals to negative GM RD parallel with R0. RD parallel with R0. So you might ask, why is it negative? Negative is because the signals are inverted. Okay, that's why you keep on seeing negative in common source. Just now negative GM RD, here now is negative GM RD parallel with R0. Okay, all good? Next one. What if I don't want my channel length modulation? I want to assume it's ideal, but now I want to consider body effect. Body effect. So when we consider body effect, remember, which means that we will have one more current source connecting between drain and source. That is my GMB VBS. GMB VBS. So in this case, I still draw the exact same thing, but I will have my GMB VBS connecting between my drain and source. Then now we examine what exactly is my VB. For NMOS, we connect all our body voltage to ground. For NMOS source over here, we connect it also to ground. So VBS now, the term VBS over here is VB minus VS. Basically, it's 0 minus 0. So this term is 0. A 0 times with GMB means it is always 0. So can we say this term we can totally ignore? Yes. Basically here, we totally ignore already. Okay. So initially, and okay, GMB. Okay, initially we got GMB VBS, but we realized that this GMB VBS in the end still equals to 0, so we ignore this term. So we rearrange. If we ignore this term, then does it look exactly the same as the initial case? Because we don't have the GMB VBS. We only got GM VGS and RD. So since they look the same, we can say that the V out over V in is just negative GMRD. So they are still the same thing. And finally, our small signal analysis, if we consider everything, we consider channel length modulation, we also consider the body effect. So we need to draw everything over here. We got GMB VBS, we got R naught, we got RD, GMV in, everything. So in this case, this is still 0, right? GMB VBS is still 0. So it looks like the second case, the one that we only consider channel length modulation. So now your gain will be negative GM, RD parallel with R naught. RD parallel with R naught. Okay, for diode connected, actually, I don't hope to start today because once we start diode connected, it will take a long time. Okay, then let's just take attendance and end today's class. I think the next class, you guys please bring your laptop. I will install LTSpice first. Okay, I'll teach you all how to use the TSMC 180 nanometer because your group assignment, your final project needs to do work on that. Okay, I'll teach you how to import inside, and then the rest you can figure out slowly. So if you have taken your attendance, you want to leave, you can leave. But I think there are 10 of you, now only 6. For those that taken, you want to leave, you can leave. Those that cannot take, you can come to me. I will mark for you. Who haven't taken attendance? Oh, Changjian haven't take. You haven't take, right? I think so because it's pending. I'll just mark for you. And then that's it, 10 people.
这里的，就是第三种情况，它为什么情况下会出现 ID 是恒定的呢？
就是 VDS 是就 saturation region，VDS 那边是平，所以那时候是稳定。
那如果这个就是借 VGS 减 VTH 是变化，那 ID 也不会恒定。
对，可是就是如果我们只看，如果我们assume我们的 ID 是一定的话，如果我们的 VGS 一直增加，所以这样子我们的那个稳定度它就不会在了，它就会 force 回去 trial region 了。就是你看。这个是 ID 稳定的时候，所以就是 VDS 大过 VDS 大过 VGS 减 VTH 的时候。可是如果它现在它是稳定着的，可是当 VGS minus VTH 它越来越大的时候，这样我的 VDS 基本上又差不多跟它一样了，它又变回来这里，所以它的 graph 就这样子。
是